Has this ever happened to you? You spend hours in the field hiking through tough terrain with limited success. Does your drone cover miles of land only to leave you with hours of footage to search through? Does your team get eye fatigue because they're staring at screens all day looking for a tiny figure? Well, get ready to sit back, relax, and have all your problems solved. EagleEye brings search and rescue into the 21st century by leveraging big data and machine learning. Using data from the University of Washington's Autonomous Flight Systems Lab, we've trained YOLO, an open source object detection algorithm to spot your missing person in nearly any photo. EagleEye makes your search and rescue mission quicker, cheaper, and safer. Check us out at eagleeye.pro to make your missions safer and faster.
Hi, my name is Matt from EagleEye, and on behalf of the entire team, I'd like to welcome you to this year's Digital University Research Day, where we'll be sharing the latest news and updates on our search and rescue software directly with you. Now, despite what the beginning of this presentation may have had you believe, getting lost is no joke. In 2017 alone, over 1,000 people got lost in Grand Canyon National Park, and this totaled up to over $1 million in damages and over 17,000 hours of spent time. And despite their best efforts, 50% of these resulted in serious injury or death. Now, when you compare the current alternative search and rescue on how to solve this problem, one would be helicopters, and that's what a lot of them use. However, helicopters are expensive and timely to get in the air. And secondly would be ground operations, which are relatively ineffective and much more time inefficient. And so then you get to the current use of drones in search and rescue, in which case drones are used. However, once you go out and collect the footage, you don't have to come and just watch it all. Normally, there's no sort of computer-assisted analysis or anything. And here at EagleEye, that's what we'd like to solve, and that's our solution to the problem. And to show you and expand upon the solution that we've done, I'm going to turn things over to Dom, who's going to give you a demo of the EagleEye software.
Hi, I'm Dom from Team EagleEye, and today I'm going to give you a look at the experience of using EagleEye for search and rescue. This is a demo of the EagleEye platform. The core concept of EagleEye is to provide a platform for search and rescue operators to quickly analyze large segments of aerial footage and find missing persons. Over here, we have a map with the exact location of the drone, as well as some useful stats, including airspeed, altitude, and heading. We use a machine learning algorithm to detect people in the video feed, making it much faster to locate them. The detection bar down here shows segments of the video where people are detected, with brighter green indicating a higher probability of detection. Instead of watching the entire video, search and rescue operators can quickly review the segments where people are detected and find their exact location. Using EagleEye, several hours of footage can be analyzed in only a few minutes.
Hi, I'm Pat. Now that Dom has shown you how the EagleEye user interface works, I'm going to talk about how the object detection works and how we have been able to test it ourselves. We are using an open source object detection algorithm called YOLO. YOLO detects people in about the same way a human does. Just as a person grows up knowing that certain types of objects are a person, or a car, or a house, YOLO is trained by looking at a data set which contains images labeled as a person, a car, or a house, and then able to tell what characteristics belong with what image, such as shape, size, color. YOLO is trained already to detect different types of objects, including people. We are building off of that algorithm by training ours off of a data set of search and rescue specific images we obtained with a collaboration from the University of Washington. This data set is composed of drone footage from wilderness areas, similar to what a real search and rescue mission might find. As you can see from this image, the normal YOLO incorrectly identifies a person as a kite, whereas ours correctly identifies it as a person. The other person isn't identified in either, but I'll talk about that later. After running our model on various images and videos we found online and confirming that it works, we decided to collect our own data and run it on that. Using a friend's recreational drone, we were able to go out twice this semester and collect our own footage. The first time was really to just establish a baseline to make sure it works. For the second time, we established an experimental procedure which allowed us to isolate different variables of interest and see how the detection varies based on those variables. These variables were things such as the height of the drone, the position the people are in, whether they're standing, sitting, laying down, whether they're moving, running, walking, or standing still, what colors they were wearing, and whether they were partially obstructed by trees, and a few others. Conducting our own experiment also enabled us to determine the false alarm rate and the probability of detection. These are the two most important metrics for judging an object detection algorithm. As you can see from our video we filmed and then ran our algorithm on, our algorithm currently detects people standing up slightly better than sitting down or laying down. But it even did detect a person who was partially obstructed by a tree. Currently, our algorithm has only been trained for short periods of time, a few hours. This is why on a previous image, you saw that it only identified one person and the other person it didn't even pick up. We are in the process of training our algorithm for a much longer periods of time, which will dramatically increase the probability of detection and decrease the false alarm rate. Doing so, we can say with confidence that our algorithm will be able to more quickly and accurately detect people than a human eye without being subject to the same fatigue.
Hi, my name is Brian, and I'd like to tell you a little bit about our journey this year. Initially just a loose amalgamation of ideas, EagleEye grew into what it is today through the guidance and care of our team's capstone class, Engineering Social Innovations. In this course, we learned human-centered design, a process which puts people first and builds the final product around their needs. Back in August, when we started this journey, our team lacked direction and struggled to find a problem we really cared about. But by interviewing professionals and listening to the feedback of our peers, we found a community worth supporting and a problem worth solving. Search and rescue professionals have some harrowing stories to share, which have moved and inspired us to envision a future in which they never have to risk their own lives when working for the life of another. To meet this end, we used Agile development methodology, a process which breaks down tasks into manageable parts and identifies problems for change. Our key takeaway from this class is twofold. Listen to your team and don't be afraid to change your design. When working together, we deserve a candid and honest dialogue, and no design, no matter how strong, can't be made better. Just like everyone else, we struggled with a virtual environment and asynchronous communication, but by maintaining those strong channels of communication and iterating incrementally, we grew EagleEye into a functional beta software in less than 2 semesters while balancing jobs, other classes, and life in general. I'd like to thank you for coming to our presentation. I hope you have a wonderful rest of your research day, and I'd now like to pass things along to Catherine.
Thank you, Brian. So that concludes our presentation, and at this point there are a number of people we need to thank. First of all, our mentor, Pete Schramm, Dr. Danik, Dr. Berman, and Christine, the Social Innovations teaching team, Jenny Laird, Wes Persino, Andrew Denoyer, Thomas Gorman for the use of his drone, Chris Hayner and the Autonomous Flight Systems Laboratory at the University of Washington for sharing data with us, all of our industry stakeholders for their advice and guidance throughout the course of this project, and finally, thanks to you for watching. But before you go, there's just one last thing we'd like to share with you.